So here, let's look at more specific confidence interval estimates. Well, we actually started off with the generic in the last video. So the generic, if you remember, is going to be that the point estimate for the lower limit, this is the point estimate minus the margin of error will give you the lower limit, and the upper limit is going to be the point estimate plus the margin of error. So it's the same thing, one's plus here and the other one's minus. And we already said the critical value times the standard error is what makes up the margin of error. So let's write this out again. So the point estimate, the margin of error is the number of standard deviations or the standard errors you need to be away from the mean to generate, say, a 95% confidence interval. And the critical value changes based on whatever the confidence interval is. So if you want a 95% confidence interval and you have a z-distribution, then this is going to be about 2 or 1.96. But if you want a 90% confidence interval, then this is going to take on a different value, which we're going to see when we start doing the examples. So that's going to be the number of standard errors you need to be away to generate a specific confidence interval, and this is going to be the same thing on the other side except with a plus sign on it. Point estimate plus critical value times the standard error. Okay, so we've got 1, 2, 3 different scenarios to look at. Now the first scenario we can look at is when the population standard deviation sigma and the population standard deviation sigma, that's that one in there, is known. Okay, then what happens? Well, when that's the case, then the point estimate, we're going to be dealing with a normal distribution, so the point estimate is going to be x bar, and the critical value is going to be z of alpha over 2. And the standard error, the population standard deviation is known. It's going to be sigma over the square root of n. So remember that this thing in here is actually called the margin of error. Critical value times standard error. This is the critical value. This is the standard error. And together, these guys are actually the margin of error. So that would be your lower limit, and your upper limit is going to be the same thing with a plus sign, x bar plus z of alpha over 2 times sigma over the square root of n. Now, that's one scenario, and we'll do examples as we move on. There's a little shortcut as well. I'll put it in for you right now, and I'll remind you of it later on as well. The margin of error, this part in here, if we just want the total calculation to be done in one go, there is in fact a function in Excel called confidence.norm, which will calculate this whole thing for you. So let's go here, confidence. In Excel, it's going to be confidence. And we're going to do an example later. Dot norm. And then it wants to know alpha. So alpha is our significance level. Even though it's alpha over 2 here, in here we put alpha. And then we need to tell it what the standard deviation is, sigma. Just the standard deviation. And then we're going to have to put in the size of the sample. And when you put that into Excel, it'll actually calculate that for you. Now, a second scenario is when the population standard deviation is not known. So when the population standard deviation, sigma, when this guy is not known, then we use something called a t distribution in place of a z distribution. I'll put down the result first and then I'll explain it to you. So it's going to be x bar minus t of alpha over 2. And there's this thing called degrees of freedom, and these degrees of freedom are n minus 1. We don't know what they are yet, but we'll figure it out, times s. Now it's not going to be sigma because we don't know sigma, so we're going to put s, the sample standard deviation, over the square root of n. And then over here, it's going to be the same thing except with a plus sign, x bar plus t of alpha over 2, n minus 1 degrees of freedom times s over the square root of n, which is the sample size. So what is this t distribution? Well, a guy over 100 years ago called Sir William Gossett, who worked for the Guinness Brewery, discovered that sometimes you have small bits of data, and when you're trying to develop a normal distribution, if your data adheres to a normal distribution, let's do a normal distribution here. If your data adheres to a normal distribution, if you've only got small samples of data to choose from to come up with your x bar distribution, those estimates, remember what x bar is, it's estimates of the population mean. If it only has small samples to estimate it with, those estimates aren't very accurate. And aren't very accurate means this. It means that you're going to get a really big spread of results. So the distribution, that's supposed to look like a normal distribution but more spread out. The distribution of t looks like a normal distribution, but it's more spread out. And in fact, the smaller your sample size is, the less accurate and the more spread out it is. So the t distribution is something that looks very similar to a normal distribution, but it's bell-shaped and it's symmetrical, but it's more spread out. And the smaller the sample size, the even more spread out it is. So they wanted to actually take the sample size into account in the calculation. So if you have a really small sample, your distribution is going to be even more spread out. The thing up here called the degrees of freedom is not just the sample size, it's the sample size minus 1. And it's the sample size minus 1. What does that mean? Well, or where does that come from at any rate? Well, let's consider this. If I have a if I'm trying to do this type of calculation, if I have a t distribution, I don't know the population standard deviation. So I actually have to estimate. If you remember the formula for this guy, it's something like the square root of the sum of xi. Because we don't know the mean, the population mean, we have to put the sample mean in its place. And that's going to be divided out and blah, 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 and squared. But at any rate, we have to estimate the sample mean, x bar, to be able to work out the sample standard deviation. So the thing is, this is not the real mean. The real mean will be this guy in here. So this is just a sample mean. But once we put in an estimate of the sample mean, it's not the real figure. It's not the population mean. It's just an estimate of it. We now have an issue because any further calculation that we do moving forward must adhere to this, if you like, fake mean we've put in here. And that constrains us. It takes away our freedom. So supposing I construct this distribution choosing samples of 3. So 1 number, 2 numbers, 3 numbers. And supposing that I find the sample mean I'm going to use in here, just for argument's sake, is 10. I'll put the 10 over here. I must now ensure that all data I choose has an average of 10. So when I pick a sample of 3, I must make sure that when I add the 3 numbers together and divide by 3 to get the average, they must equal 10. This fake mean, we must continue to adhere to it. So I have total freedom in choosing this first number. Supposing this first number is 12. I have total freedom in picking this second number. It may be 7. But picking this third number, I have no freedom because I have to make sure that this third number actually makes sure that the average of these guys comes to 10. So this number, whether I like it or not, has to be 11. I have no choice. Okay, so I have no freedom in choosing this number. So even though I'm picking samples of size n equals 3, that's the sample size, the freedom I have in choosing is reduced to, I can only choose 2 numbers freely. So the degrees of freedom, the freedom I have is in choosing n minus 1. n minus 1 is 2. I have freedom in choosing 2 numbers freely. Okay, so just generally speaking, every time you put on a constraint, which is basically you putting in a false figure into the calculations because you don't have the real figure, what actually ends up happening is that constraint reduces your freedom or flexibility in carrying out further calculations. And the way we actually take account of it is up here. Okay, so sometimes I tell students that one way of actually doing this, figuring this out, or try to understand this, is like when you tell a lie. Like if you're going to go out somewhere and you're not telling the truth to your parents or your partner where you're going to go, you have to make sure that everybody, all your other friends, are aware of this lie. So you have to be consistent with it, and it's the same with the putting a constraint. The constraint is not the real figure, it's an estimate. So you have to be consistent with it and stick to the story, as it were. So another thing I can actually put in here for you is that this in here is the actual margin of error for this case. We're using the t-distribution. And again, there's a function in Excel that works this out in one go for you. And that's going to be not confidence.norm, but confidence.t. So we can actually put that in as, you can go into Excel and do confidence.t. It's kind of good because it actually does a lot of the calculation for you. So it's confidence.t, that's the C, confidence.t, and again we're going to put alpha, which is the significance level, and the sample standard deviation, and the sample size. And you put that into Excel, and that will actually give you, in one fell swoop, the margin of error. And do we have any other cases? Yes, we do. We have one more case, one more scenario, and that's for proportions. Just as we had proportions before. So if you remember for proportions that we looked at earlier, for us to be able to use the normal distribution, which is what we're doing for the proportions, we have to ensure that n times p is greater than or equal to 5. And also that n times 1 minus p is greater than or equal to 5. Both these conditions must hold for us to be able to use what I'm going to show you below. So remember, all we're going to do for the confidence interval for proportions, we're still going to use this, point estimates, plus or minus the critical value times the standard error. So what is the point estimate for a proportion question? Well, the point estimate is just going to be p bar. And the margin of error is going to be the critical value times the standard error. And so minus, what's the critical value going to be? Well, we said once this is true, this means we have a normal distribution. So this is just going to be z of alpha over 2. and we're going to multiply that by the standard error. And if you remember what the standard error is, it's going to be, for a proportion, it's going to be p bar times 1 minus p bar divided by n. And the upper limit is going to be exactly the same thing over here. It's going to be p bar plus z of alpha over 2 times the square root of p bar times 1 minus p bar over n. So this is the three scenarios you have for working out confidence intervals.